To build continuously compounding AI agents, we must stop hand-coding static simulators and start dynamically wrapping them. Reinforcement learning and autonomous large language models depend entirely on interactive environments to secure reward feedback and validate their skills. The environment dictates the limits of what the agent can learn. Look at the current standard. Evaluation benchmarks like SWE-bench, WebArena, and AlfWorld are monolithic, static, and painstakingly hand-built. This creates severe bottlenecks. First, these worlds are blind, presenting fixed challenges that cannot adapt to probe an evolving policy's weaknesses. Second, constructing realistic sandboxes requires months of human engineering to configure file systems, containers, and testing infrastructure from scratch. Finally, foundation models are outgrowing these environments, reaching capability plateaus where static tasks no longer provide a meaningful challenge. Because these environments cannot evolve, they create a hard ceiling on reinforcement learning gradients. This forces a dead end in agent capability scaling. To bypass this bottleneck, we need to shift our focus to how we currently engineer the agents themselves. Developers rarely alter the internal weights of a foundation model to create an agent. Instead, they wrap a frozen large language model with an agent harness, a layer providing execution loops, external tools, and memory. If we freeze the model and shape its behavior with an external wrapper, we can apply that exact logic to the static environment. EnvHarness is the realization of this symmetry. It is a programmable middleware layer that sits entirely outside the simulator. EnvHarness intercepts the agent's actions and reshapes the interaction behavior of the environment on the fly. It accomplishes this without altering a single line of the original backend simulator code. Treating the environment as a frozen backend that we manipulate with modular software wrappers provides the necessary mechanism to unblock agent learning. Traditional attempts at automated environment generation try to synthesize entirely new task instances from scratch. The fatal flaw in these synthetic pipelines is their reliance on noisy automated verifiers, which frequently hallucinate success rewards and corrupt the training data. Looking at the EnvHarness architecture schematic, we see how it circumvents this issue. It operates exclusively by intercepting standard interface functions, like the initial reset and action steps. By only wrapping the interface, the original hand-coded reward function remains completely isolated and rigorously unmodified. This establishes the core guarantee of the EnvHarness paradigm: zero reward hallucination. Researchers can generate thousands of unique task variations while trusting that every success signal generated during training is mathematically real. Decoupling interaction dynamics from ground truth evaluation provides a reliable, scalable foundation for complex policy training. The environment wrapper itself is built from three distinct plugin components. First is the stage component, an initial state manipulator. Instead of a default starting position, Stage pre-executes physical actions immediately after the reset function. In a physical reasoning task like AlfWorld, it might silently open a drawer and hide the target object inside, forcing the agent to learn exploratory search capabilities. Second is the contract component. This rewrites the interaction interface directly. During step executions, a contract layer can inject network delays, simulate sensory noise, or mask specific DOM elements on a web page to rigorously test the agent's perceptual robustness. Finally, the chain component acts as a multi-environment composer. Chain connects completely distinct environments into a workflow. It can take data scraped by an agent in a web navigation task and pass it directly into a separate spreadsheet environment for tabular analysis. By nesting stage, contract, and chain layers together, researchers assemble highly sophisticated adversarial curricula from simple static bases. While these modular wrappers are highly effective, hand configuring them for thousands of tasks is slow and labor-intensive. To close the loop, the system uses an algorithm called NRigor, an automation engine designed to synthesize these wrappers through trajectory inspection. In Phase 1, flaw diagnosis, NRigor observes successful and failed agent rollouts to pinpoint specific behavioral weaknesses. Next, in component synthesis, a large language model authors targeted stage and contract configurations designed explicitly to exploit that exact diagnosed flaw. Finally, in verification, the new environment undergoes a fresh rollout test. It is only admitted to the training pool if it remains solvable. NRigor guarantees a closed-loop ecosystem. The environment dynamically evolves to expose the agent's active vulnerabilities. To prove the efficacy of this system, researchers evaluated EnvHarness across 5 demanding benchmarks, spanning software engineering, tabular reasoning, and physical manipulation. This data table illustrates a clear performance gap. EnvHarness-trained agents consistently outperform base models across all tested domains. In held-out AlphaWorld tasks, EnvHarness models jumped 9 points, proving exceptional generalizability. In complex software engineering on SWE-bench verified, they logged a 4.9-point increase. Standard training regimens face a specific bottleneck, scaling limits. Static synthetic environments, like those generated by SWE-Smith, plateau rapidly after generating roughly 100 tasks. This graph tracks the difference. NRigor maintains a continuous capability curve well past 300 environments. By tailoring novel challenges directly to the agent's current skill level, EnvHarness provides the mechanism for continuous capability scaling. Operational benefits extend beyond higher task completion rates. Reinforcement learning algorithms thrive on dense optimization signals. Synthesizing targeted stage obstacles produces a denser, step-by-step curriculum, yielding up to 6.5 points of policy improvement over baseline reinforcement learning methods. This creates intense execution efficiency. Agents trained in these rigorous, perturbed environments execute production tasks using 9.8% fewer steps. Exposure to robust preconditions forces the policy to abandon meandering trial-and-error behaviors and internalize direct, purposeful action plans. We no longer need to endlessly rebuild rigid simulators from scratch to create advanced training curricula. The solution relies on 3 pillars: modular programmability that preserves ground truth verifiers, automated co-evolutionary loops targeting specific behavioral flaws, and extreme operational step efficiency. Relight the environment to adapt to the agent, and the agent's capabilities can continue to expand through previously insurmountable plateaus.